And I'm going to turn things over now. Thank you everyone for joining us this evening. I am Karen Greenhouse, the Professional Development Manager here at Key. We have Scott Steckety from KCP Technologies who is going to be doing our presentation today, so thank you, Scott. And also online we have Elizabeth DeCarly, one of our managing editors, who is going to be helping me answer questions while Scott is doing the presentation. And so I'm going to turn things over to Scott right now. So Scott, there you go.
Okay, welcome everyone. I want to clarify one thing I said earlier, that the presentation sketch, which you will get as part of the zip file, can be opened using only Sketchpad 5. I do want to make it clear that everyone, even if you don't own Sketchpad 5, can download the demonstration version of Sketchpad 5 and use it to look at anything that we've done today. So let's begin. And I have a number of things that I find absolutely fascinating, and I hope you'll find them nearly as much as I do, that we can do with Sketchpad's iterate command. We're going to use some sequences to explore functions. We'll explore some limits. We'll model some real-world phenomena, and we'll create some really lovely images. If we have time at the end, we'll also evaluate e to the I pi. I don't think we had pictures before, so these are the pictures of the folks who are with us today. I'm there at the top as the presenter, and Elizabeth DeCarly will be answering questions, and Karen is our MC. And I want to say a couple things as we begin about why iteration matters to us in exploring important mathematical ideas. And one way is that it lets students explore functions in a powerful way that, that gives them one more representation, one more way of thinking about functions. By making steps smaller in a mathematical process, or the number of steps larger, we get to explore limits. Modeling of real-world phenomena often requires repeating steps many, many, many times, so iteration is great for that. And we're going to create some really lovely images. So, first I want to start with a poll, and I think I can make this work. Karen will help me if I have any trouble doing this.
Okay.
Oh, click launch.
There you go.
I did get it.
All right.
And if you'll indicate which of those types of sequences you use.
And a couple things while we're waiting, Scott, just so people know that if the presentation screen looks kind of small on your computer, up at the top you should see a button kind of next to the X. There's a bar across the top that says Go to Webinar Viewer. If you click the expand next to the X, that should enlarge it to fill your entire screen. So just in case someone has a really small screen on, that's something to remember.
Okay. So as it turns out, lots and lots of people make use of arithmetic and geometric sequences to explore functions. And let's take a look at doing some of that with Sketchpad. So I've got here a blank screen, and we're going to create a couple of sequences and look at them as functions. So let's begin with an arithmetic sequence. Let's, for instance, take the value of y and add 2. And to keep track of the index of the sequence, we'll use the value of x for that. So we'll calculate x plus 1. So the index of the sequence will go up with each step, and the value of y will go up by 2. So by selecting those two values and choosing iterate from the transform menu, we get to iterate the value of x to x plus 1, the value of y to y plus 2, and we see 3, 5, 7, 9 are the values that come up as part of our function. So it would have helped if I had ordered these in the opposite order. I'll do that in a moment. We're going to repeat this now with a graph and take a look at how this turns into a graph. So let me delete that for the moment, show a coordinate system here, and I'm going to redo the y calculation just to get the order in the table correct. Okay. So we'd like to graph this point, graph that as xy, and we'll also graph the original 0, 1, and let's connect those with a line, and now see what our iteration looks like. So we get to see how the iteration develops, and by increasing the number of elements in the iteration, which I can do by selecting any portion of the iteration and pressing the plus sign, we get to see how that arithmetic sequence progresses. Now, if we'd like to take a look at different possible arithmetic sequences, we can easily change our calculation. Instead of y plus 2, let's do y plus 1. See what happens there. What if we did, instead of y plus 1, y minus 1? Oh, let's see what happened to that. Oh, there we go. Okay. So we get to explore lots of different possibilities here very, very easily. And in fact, if we want, instead of y plus 1 or y minus 1, to look at a geometric sequence, we can do that as well. So we could do, for instance, y times 2. Oh my, that goes up very, very quickly, doesn't it? Let's try something that's not quite increasing quite so fast. How about y times 1.1, let's say. Okay. And let's look at a lot more of those. And we could explore what kind of a function we get from a geometric sequence like this. And in fact, if we like, we could explore whether this turns into whether this looks more like a parabola or whether it looks like some other kind of function. In fact, what we have here is an exponential function. If we wanted to get from this a quadratic function, we'd have to explore a little bit different kind of iteration here. Let's take a look at what happens if, instead of multiplying, instead of adding, we add some other number. Let me create a new parameter, which I'll call d for the difference. And each time, let's increase the value of y by that difference. Plus the difference, okay. And let's start y this time with 0. And let's make that difference increase by 2 each time. Well, let's take a look at what happens with this iteration instead. So we're going to iterate x to x plus 1, y to y plus d, and d to d plus 2. Okay. And we can look at this in a little bit more detail here by changing the scale. So if we made, we use 50 pixels, if 100 pixels represents 50 on the y-axis, we get to see the graph a little bit better, and we can extend it a little bit more. And we can see what we get when we create a sequence that has a constant second difference. Okay, I'm going to show a Fibonacci sequence very quickly.
Scott, can I interrupt? We have lots of questions, I think, that relate to this sketch real quick. So if you maybe could answer those first before you move on.
Sure.
All right, so the first one is why, wait, let me make sure I have my time correct here. Why do you have to use both, wait, how did you define x and y initially, and why both to make an x variable for the index if the iterate command is automatically creating an n for you?
The first question, how did I create the x and the y? I simply created both of those as parameters, new parameter x, and I was using integers, so I typed an integer for the value, and by changing that to just plain 1 rather than 1.00, the advantage of changing it to 1 is that it automatically comes up with a precision of units rather than of hundredths.
Okay.
So that's an advantage there, and I did the same thing with y. Now the second question was, why did I use x to essentially duplicate the index of the iteration? So we have an index of the iteration over here which exactly matches the value of x, which doesn't actually show up in the table. And the reason I did that was because I wanted to be able to graph the x and y values.
Okay.
And we don't have a way of graphing the value of n because it doesn't exist as a parameter in the sketch.
Oh, now that may have answered my next question, which is there a way to tell it to use n as the horizontal axis?
Right. There's there is a more limited way to tell it to use the value of n. Indeed, I could do that. And the more limited way is this. Let me get rid of the graph that I have here. And let me do this with just y and d. So I'll iterate y to y plus d, d to d plus 2. So now I have n as my only index, right?
Mm-hmm.
And I can, with the table selected, I can graph the table data. And that actually uses n and y plus d as my as the points that I graph. The disadvantage of that is that these are actual individual points. Each point is graphed at a particular value from the table. So if I look at the properties of that point, it's actually the point 9/100. And the disadvantage of that is that if I now go back and make a change, so that, for instance, if I added 3 and made my second difference 3 instead of 2, although my table changes, I have the original graph over here. Now, that's convenient if what I want to do is compare two sets of data. So I could plot that table data as well. Notice, by the way, when you plot table data that has more than 2 columns, you get the choice. I'm going to use the value of n as the x value, and I'm going to use y plus d as the y value. I could choose the third column, the second difference, but I'm just going to plot the n and y plus d. So I could graph them, and by changing color, I could make it convenient to compare what I had the first time with what I had the second time. But these actual points now are all fixed. They don't change when the table changes. That's why I used x and y, so that I had something that would change when I changed to a different type of sequence.
Okay, good answer. One more question before we let you move on. It says, can Sketchpad find a function by regression like a calculator can?
We can, yes.
Okay.
We have a number of activities in Sketchpad Lesson Link in which we do various kinds of curve fitting, linear regression, fitting to a variety of different curves. There's an activity in which you take a look at, you get certain data on your screen and you have to decide, does this look like a periodic function? Does it look like a quadratic function? Might it be an exponential function rather than quadratic? And you choose which of the functions it is, and you engage in matching the data to that function. So we're not just limited to linear regression. We can do anything that match to any kind of curve that we want, but that's not a native capability of Sketchpad. That's something that's explored in several of our Sketchpad Lesson Link activities.
All right, thank you.
I noticed one other question about the box around the parameters. The box appears automatically in Sketchpad 5, and it just makes it an easy way to change the initial value of a parameter. So for instance, if I wanted the initial second difference here before I start incrementing it to start at 4, I can just type 4 in the box, and just makes it easy to change parameters.
Okay.
Okay.
Thank you, Scott.
All right. I might just skip I'm going to skip some of, I'm not going to explore all the details of Fibonacci that I was thinking about, but let's do a quick exploration here by plotting the current value of the sequence against the next value of the sequence before I iterate. So I'm going to plot that as an XY pair. And I'm also going to plot this point as well, because I'd like to connect these two and find the slope. And the slope there is 0. I see that I have 0 with no decimal points after it, and I'm going to change the units so we get to see this number to, let's say, 10 thousandths, and it's still 0 is still 0. Okay. Let's now go ahead and see what happens if we iterate. A and B, transform, iterate, and A is going to map to the value of B, and B is going to map to A plus B. So what we've done is we've taken B is now in the second step, B will now be the sum, and A will be the value that B used to be. So by doing that iteration, we get to generate the Fibonacci sequence, because each term is the sum of the two previous terms. So with the table selected, and I should have talked about this before, with the table selected, there are several ways to increase iterations. One is the context menu, right-click or control-click, and you can increase the number of iterations. Another way to increase the number of iterations is to right-click or control-click, choose Properties, and in the iteration panel, say how many iterates you want. So now we have 10 of them. And yet another way is to select the table or any element of the iteration. And on the keyboard, press either the plus key or the minus key to change the number of elements that you see in the iteration. So that's a fundamental ability with iterations that makes it pretty easy to change the number of iterates you have. Now, the fascinating thing for me about the Fibonacci sequence is all the different connections that it produces. Oh my goodness, it's astounding. And one of the interesting connections here is this value for the slope of the Fibonacci sequence seems to go to a very clear limit. It's obviously getting close to 1.6180 something. And I think I've seen that number before. Let me think. Something like 1 plus the square root of 5 over 2. Can that be the number? Let's look at this one to 4 decimal places. And my goodness, it does seem to be the golden ratio. So the connection between the Fibonacci numbers and the golden ratio is really a very interesting connection to me. Okay. So those are a few functions. This, we've seen some exponential functions, some linear functions, some quadratic functions coming out of sequences. Let's get into some stuff that's a little bit sexier here. And I would like to begin this with another poll. Actually, I should stop and see if anybody has any questions.
There is one that just came up. It says, can you say exactly what steps need to be taken to define an iteration?
Yes. Okay, and let me hit that on the very next iteration we do.
Okay. And then there's a question from Steve asking if you can change the precision level displayed on the table.
Absolutely. We
yes.
can change the precision in the table because the table is live. So if I were to change the properties of the slope measurement here to show instead of 10,000s to show 100,000s, so we'll show 5 digits of accuracy rather than 4 in the value from which the table is created. And the table then shows those values as well.
Thank you.
So the table actually tracks the precision in the measurement from which it's made. Okay, my second poll. Which of the following sequences do you use to help students understand limits? Wait a minute. Is that right? Yes, that is right. I'm sorry. I'm slow on pushing the launch poll button. Everyone sees the poll now, I believe, right?
Yes, they do.
Thanks.
And so and they're responding very quickly. Look at that. And just so you know, you can choose more than one answer in this poll. So whichever one you actually use, all, any, none. And okay, I think you can probably close the poll. There you go.
Okay. And lots of folks do use sequences to look at derivatives and accumulation of value. Not so many with antiderivatives. So let's explore a way in which iteration lets us get at some of the limit concepts that are involved with derivatives, antiderivatives, and accumulating value. I do want to do want to observe, somebody pointed out a curiosity in the table here where the 15th row is 804 rather than 803. And one of the things you may notice is that the values increase and then decrease, increase and decrease as they're centering in on the final limit. So I think that's the reason why we have an 804 here. So it's interesting. Okay, derivatives. All right. So what I have here is I've prepared a graph of a particular function, ax cubed plus bx squared and so forth. I've used parameters to define the function, so we could change the value of a, for instance, using my plus sign or minus sign to change the function any way we want. So we have the ability to look at all kinds of different functions here. And when you get this sketch, there are some directions here that describe what I'm going to do. And what we want to do right here is figure out how the slope of this function changes at different places on the graph. So what we're going to do is we're going to take an interval along the graph, and that's what the value of h is going to be for. And I've already measured the value of x, and I've evaluated f of x at that value. So if we want an interval of 1, I create x plus h to show where the interval ends. Starts at 0.4, will end at 1.4. And I'd like to know what the value of the function is at this new value of x. So with the calculator, I click on the function, and I click on the value at which I want to evaluate that function. So now I have a new value of x and the corresponding value of y. So I can plot that as an xy pair. And let's see, I'm looking to find the slope over this interval. If I wanted to draw a slope triangle here, I would need the point right there at the right angle of the slope triangle, and that point is going to be given by the new value of x and the old value of y. So let me graph that as well. And now actually use the polygon tool to create the slope triangle. And so it doesn't clutter the sketch too much, I'm going to make the line style here a thin line. And we can see that as we move A to different points, we do have the slope triangle tracking what we're doing. I might just hide this point because I don't much care about that point. The triangle is what's important. And I could take that segment and measure its slope, but I don't want students to do that. I don't want students to do that because I want them to use the slope formula to find it for reasons that will become clear. So I just press the delete key to get rid of that last calculation that I did. I don't like the R here. I'm going to change that to B. I think that makes more sense. So let's go ahead and use the slope formula on this. Let's see. To calculate the slope, we need the rise over the run. And the rise is going to be the y value at point B minus the y value minus the value of the function at point A. So by subtracting the value of the function at A from the value of the function at B, that should give us the rise. The run, similarly, will be the new x value minus, oh, you know what? It's easier if I just say the run is the value of h, because that's what I've added to x. Okay. And now I can calculate the rise over the run. So that's going to be f of x plus h minus f of x over h. So that's going to be the slope. And I'd like to show that slope. So that slope is the average slope for this interval. And to show that slope for the interval, I'm going to plot the original x value and the slope. So I'll plot that as xy. So that shows the value of the slope here at the start of the interval. And I'd like to show that that's the average slope over the whole interval. So I'm going to plot one more point. At the right-hand end of the interval, I will also plot that same value for the slope and connect these two with a segment. So this is the value of the slope over this interval, and we can drag here and see how the average slope changes for that interval at different places along the curve. All right, so we're finally ready to iterate. Let's go ahead and do that. What are we going to have to iterate? It's just going to be the only thing that changes is point A. Point A controls the whole construction. So I'm thinking now about what I need to select in order to iterate. Since point A controls the whole construction, if I iterate point A to point B, I'll get the entire construction of the slope triangle, of this segment, and all of these calculations repeated at point B and at the next point and the next point. So for this iteration, I need to select only point A. Let's go ahead and iterate point A to point B. And Sketchpad normally begins an iteration with three new values. So I'll click Iterate, and with the iteration selected, I can choose the plus sign to increase the number of iterations as much as I like. And we get to see lots of slope triangles, lots of average slopes. The average slope within this interval is given right here, and so forth. Okay, I'm going to get rid of the table because I don't really care about the numbers. I'm much more interested right now in what's going to happen with the picture. I want to develop a picture in my student's mind of what happens when we look at the average slope and make the intervals smaller and smaller. So to make the interval smaller, the interval width is h. So with the minus sign, I can use the minus sign on a parameter to reduce its value, just as I use the minus sign on the iteration to reduce the number of iterations. A minus sign on the parameter will change the value of the parameter. So let me reduce this, and gee, I find as I reduce the width of the interval, I really need more iterations. So now I'm back to the plus sign to increase the number of slope triangles and so forth that I have here. And let's accelerate the process a little bit. Let me just jump down to, let's say, 0.2 for the value of h. And let's accelerate the process here for the slope triangle by going to Properties, Iteration, and instead of 35 iterations, let's be on the safe side. We might need a lot. Let's do 1,000. We don't care about the ones that we don't see that are off the screen, so make them as many as we like. And now let me do one more thing to simplify the image that we're seeing here. I'm going to select the two endpoints of these iterated segments and press the delete key so that we only see the segment itself, because that's really our indication of what the slope is, the average slope for this portion of the graph. So now let's make h a little smaller and smaller and smaller. That's interesting. Let's make it even smaller. Uh-oh. Oh no. we can't make h 0 or the whole process doesn't work. So let me go back to 1/100th, and we see what we get for the average slope when intervals are only 1/100th. If I wanted to make it even smaller, I could make it 1/1000th. Let me do that. The value I'm going to change to, make it 10 thousandths in case I ever want to go smaller than that. And I can change the value here too. Okay. So 0.01, they're even smaller. And once again, I don't have enough iterations. I made it 1,000. Let me make it 10,000. Oh, 20,000. Make sure that we're covered here. And we get to see, as we get smaller and smaller with the interval, what happens to the derivative, that it really is approaching a limit. As h becomes small, it really is well defined. So I can see, for instance, if I change this from 1,000th to 2,000ths, watch how much change there is when I click outside the box in the derivative. Nothing that's visible. So we really see how this does approach a limit. All right. Are there any questions before I show a couple of quick things related to derivative and antiderivative?
There's just one main question. It says, how does the program know that the parameters of the cubic aren't also part of the iteration?
When I choose, well, in fact, let me say this. The parameters of the cubic are part of the iteration in this sense, that if I change one of these parameters, it's not just the function that changes, but the derivative as well. So in that sense, these parameters all affect the iteration in just the same way that h does. H affects the derivative, these affect the function, all can affect the result. But they're not required to create the iteration. What I select when I choose iterate, that is the thing that is actually iterated, that is actually changed during the process of the iteration. So the position of point A is iterated all the way along this function. These values don't need to be changed. It's only the value that needs to be changed that we iterate.
Okay.
I don't know if that explained it well or not.
No, Steve says he got it, so that's good.
Okay, cool. All right. I'm going to make this real quick on these. I've got some tools here that I'm going to use the tools real quick. So this is antiderivative. I'm going to create an antiderivative probe that will just show me measurement F. Oh dear. I'm not sure what measurement that's supposed to be. I may just skip this. I know what happened. That probe isn't working right. Don't worry about it. I'm going to skip both of these because I want to go on to real-world modeling right now. And let me ask another quick poll. Which of the following examples of motion do you use to model real-world problems? Do you use any of these? I'm going to show you all three. So interestingly, we have lots of people who use projectile motion. And I'm going to close the poll prematurely because I want to hurry because I've got too much cool stuff to show you still. All right. So lots and lots of people use projectile motion, carousel, circular motion, a fair number of people use, and orbital motion as well. A lot of people use a lot of these things. Okay. So let's take a quick look at a projectile motion experiment with iteration here. And what I have I'm only going to do the first of these. We have on the screen two vectors, a vector for the g, the acceleration of gravity, and a vector for the initial velocity of a point. And the activity that's going to be included will allow you to construct all this with Scratch, from scratch. You'll have a worksheet and activity notes in your zip file that describe this entire process. This is one of our Sketchpad lesson link activities. But I'm just showing the demonstration here quickly. So I've got the construction here, and with this construction, we're going to take P naught and use the initial velocity to figure out what its new position should be at the end of the first time period. Now, because we have gravity acting, that's also going to change the velocity because gravity affects velocity. So the gravity being downward is going to move the velocity in a downward direction, so the new velocity is also going to be changed. Not only the position is changed, but the velocity is changed. So now we're going to iterate, and to iterate, we're going to select the initial position and the initial velocity because both of these points need to take on new values for the next step of the iteration. In fact, the next step of the iteration is going to need to use this new velocity v1, and it's also going to need to start from the new position p1. I don't select g because the gravity doesn't change, so I don't need to select that. So let's go ahead and choose iterate, and p naught goes to p1. Notice initially it's still going with the same velocity each time because I haven't mapped the velocity to anything different yet, but I'm about to map the velocity to v1. And we can now, did I do something wrong here? I may have something wrong in this. I don't know quite what I did here. So this is embarrassing. I may show you the second instance, which I think does not have any errors in it. Let me just double check and make sure that this is not behaving the way it's supposed to behave. So I don't know what I did wrong the first time. I have no idea. Okay. But there we have the second step with the new velocity, a third step with yet a different velocity, and so forth. And by increasing the number of iterations, we get to see how the velocity changes, and we get to see how the position changes. And the second page of this example is going to give you the opportunity to change not only the velocity and the position, but also to change the value of delta t. On this first page, we're stuck with delta t equals 1. On the second page, goes where the activity itself goes and takes you to delta t equals 2 and so forth. Okay. Another real-world problem. Carousel. So, on this carousel, I'm going to put 9 horses, and I've already got some calculations set up ahead of time. By dividing 360 by 9, every horse is going to require 40 degrees of the carousel circle. And I have a ratio here, which I'll show you what it does in a moment. But the basic idea is I'm going to take point A, I'm going to rotate it by this angle, and I'm also going to rotate it by the second angle. And you can see that the ratio actually says how much of that 40 degrees is the horse going to take up. So we're going to put the horse between point A and this point that's affected by the ratio. And let's construct some perpendicular lines here, and I didn't mean to have point H selected, so I'll get rid of that extra perpendicular line. And now I'm ready to put the horse in place. So I'll put a point here, I'll put another point here, and I'll put a point here. And with those points, I'm going to select my horse, copy it, and this width and this height, I'm going to paste it. That was weird.
Scott, I think you hit clear instead of paste.
I hit clear instead of paste.
Yeah.
Okay. There we go. Thank you, Karen.
You're welcome.
Embarrassing when one does that, isn't it? So because these perpendiculars get closer together, it does look like the horse is turning at the ends of the carousel. So that's good. And let's see what I need to do to make more horses. Let's see, another horse ought to begin here, following my first horse. And I'm going to need, since I have 9 horses total, I'm going to need 8 more to complete my carousel. So this is the first example we've seen in which I select both the point to iterate and the depth of the iteration. Holding the Shift key down, I choose Iterate to Depth, and point A gets iterated to this point here, okay, and that will be exactly 8 horses. I'm going to delete the extra construction lines that developed from the iteration, and here are our horses. Now this carousel is slightly confusing because which horse is in front of which other horse has no relationship to where we are around the carousel. In fact, the very last horse in the iteration is in front of all the other horses, no matter where he is, even when he's supposed to be behind. So I've got a second construction here, and I'll give you, part of the zip file will be directions on how to create this yourself. What I've done on this second one is I've made some horses that are in front and other horses that are behind, so that we have the true illusion that we're looking for, with the horses in front always staying in front and the horses behind always staying behind, no matter where they go around the carousel. So that's a fun one, and you'll have the entire sketch to work from. All right, I've run out of time to show all the details I wanted to show, so I'm just going to run through a couple of demonstrations very quickly to let you know what's in the rest of this sketch. This is a simulation of 3 stars. We have 3 stars, masses 7, 5, and 3. You've heard of binary star systems, I'm sure. You may not know why there are no triple star systems. So I've got initial velocities for all 3 stars here. Let's start the iteration and see what happens with these 3 stars as they orbit each other. And there doesn't seem to be anything terribly regular about this process, does there? My. And in fact, it looks like our 3-star system has just disintegrated. These traces over here, by the way, are the traces of the velocity vectors. If we only want to look at the paths of the stars, we can get rid of them. And we really have, the system is totally self-destructed. A planet and binary star, on the other hand, the planet is much smaller than the stars, so we get to see how the binary stars can orbit each other in a reasonably stable way, while a planet encircles the center of mass of the binary system. So we get to see here why binary systems are reasonably common, but triple star systems do not exist in the universe. So that's an interesting use of iteration. I was going to show you a couple of examples of Sierpinski triangle. I'm going to make it just one. Take a look at how easy it is to construct a Sierpinski triangle. Construct that triangle, construct the midpoints, and selecting the three vertices, I can simply tell Sketchpad, okay, iterate first. First I'm going to repeat the triangle down here in this corner. So point A, the selected one there, goes to here. Point B goes to where it is. Point C goes over there. And now I'm going to add a new map. And this time I'll do the lower right. Point A, point B, point C. And let me add yet another map. Point A stays where it is. Point B, point C. And to make the results look a little nicer, we'll change the line style to hairline, and we'll increase the number of iterations. So we get a very nice picture of the Sierpinski triangle. One last thing I'm going to show is an iterated function system. This again is a Sketchpad lesson link activity which comes with this all set up. The relevant thing here is that we're using the coordinates of P to calculate 4 different sets of new coordinates based on some coefficients here. And we have a point here which gives values, which changes which of these 4 equations we're using. So right now we're using the 4th one because point C is all the way to the right. If point C is all the way to the left, we're using 0 and point 24. Oh no, that's not right. Hold on. 0 and point 47 when C is to the right, and we'll use the other 2 at various times. So we're going to iterate point P to point Q and see what happens. And we're also going to iterate C to itself, and I'll explain why in a second. So let's iterate those. P to Q, C to itself. Don't need the table. And we get to see that the particular set of equations that we're using right now, this one right here, calculates something that seems to go towards a limit up in this direction. And that's because point C is always using the 4th of those equations. Now it's using the 3rd equation. And dragging C some more, the 2nd equation. So we see that each of the equations produces a rather different result for the behavior of this iterated function. So now we're going to do one more thing. We're going to look at the properties of this iteration, and instead of point C always going to the same location, instead of it always using, for instance, the 4th set of equations, we'll let it randomly choose which of those it goes to. And we get a very confusing mess of points here. If I increase the number of points, we can see the 4th one sometimes leading back up towards that attractor that it seemed to go to. So let's look at a lot more. And to look at a lot more, I'm going to change the points to make them really small. And a lot more, to my way of thinking, means, let's say, 2,000. That's a good start. And we seem to be developing some sort of a picture here. So let's push our luck a bit and go from 2,000 to 20,000. and we get to see the sort of picture that this iterated function system produces. And I just can't resist turning that green as a fern that's springing up in the early days of spring. So those are the activities that I had time to show you. E to the I pi is in here also, which is very nice.
Is that a quick one, Scott? Because you had a request for that one specifically.
Oh, I did.
You did.
Yes, I can do it pretty quickly. I can just give a quick rundown. The first page explores some limit questions and some conclusions that include, and we're not going to go through these, but the limit formulation, E is the limit of this value, and when you raise it to a power, it makes this change, and so from that we can get this. So we're going to jump over to e to the I pi, and I'm not going to go through the multiplication process here, but that's the directions here for doing that are right here. What we're going to do is take a value z and multiply it by 1 plus I pi over n. So the third page shows the results of that process. And here is 1 plus I pi over n, right here on the graph. We have the calculations needed to do the multiplication right here. So we've taken z and we've multiplied it by 1 plus I pi over n. Everything else is shown as a vector here. I really should show this is a vector as well. So there it is. The product of this vector and this vector gives us z prime. And let me remove the iteration from that and show you how I iterated it. All I need to do is take point z this many times, and by mapping to z prime, right, z prime is the product of z and 1 plus I pi over n. So if I do that n minus 1 times, that multiplication, I will get 1 plus I pi over n to the nth power. So I've done it once, n minus 1 more times, transform, iterate. So iterate point z to here. Oops, my mistake. I forgot to hold the shift key down to get iterate to depth. Transform, iterate to depth. Now this time I'll do it 9 times. There we go, 9 times. That's good. So go ahead with the iteration and get rid of the table. Now this is some arbitrary value z that's multiplied by 1 plus I pi over n to the n power. And to find this limit, I want that number itself, not some arbitrary value multiplied by it. So I'm going to start my arbitrary value at 1, and I get to see now what, let's see, there we go. I think you can see it ends up over there somewhere. Okay. And let's see what happens as we increase the value of n. So we're up to 20 now. And that's an interesting change. I don't know. What have I just done here? I want to drag the whole thing. There we go. Okay. So I'm up to 20. I better make these guys hairlines and get rid of the ones I don't want there. And I'm also going to select this point. I can get the terminal point. In an iteration, I can construct the terminal point of any iteration by selecting the iterated image and asking for the terminal point. So if I construct that line as well, that shows the end of this process. I'll make that nice and thick because that's a pretty important line. And now let's see what happens if I go to, let's say, 200 iterations. And it certainly looks like 200 iterations of this product takes us very, very close to -1. Where would we end up with 2,000 iterations?
Wow.
e to the I pi is -1. Oh my goodness. So I've gone over. I'm sorry about that.
No, that's okay. There is one question. Let's see. Oh, is this the Archimedean spiral or the logarithmic spiral?
I haven't thought about it as a spiral. I mean, it clearly is with a with fewer iterations. So it's a spiral that results from multiplying each time. The angle is identical each time, but it's a constant ratio. So I'm not sure.
We'll figure it out. We'll figure it out. Okay, so in essence of time, I know some people have to go. Can you go to your last page? There's a couple questions that, if you don't mind, we stay on and answer them, but I just want to make sure that those people who need to go get the information. We are going to post a zip file of this webinar, which is, what exactly, Scott? It's the sketch and...
The zip file is going to include the presentation sketch and those activities that I showed that are in Sketchpad lesson link.
Are you including the teacher notes as well for the activities?
I will include the teacher notes for at least some of them. I'm not sure if I'll include them for all of them. I want to leave some inducement to people to subscribe to Sketchpad lesson link, but most of them will have teacher notes. For sure.
Okay. And then the recording will also be posted. It usually takes about 2 days for me to get that up onto our website. So by Thursday, the recording and the zip file will be up at keypress.com/webinars, and you just look under archives. You'll see all of our archived recordings there, and you can view the recordings and download the zip files for all the previous Sketchpad webinars we've done, plus this one. Sketchpad lesson link that Scott's mentioning also is our online curriculum database, and so there are sketches that do the iterations, do regression, all those types of things that come up. And Scott, did you include the promotion for today on your slide, or do I just need to send that in?
No, I didn't get that. Do you want to?
Okay, no, that's fine. Just so you know, you all will receive a follow-up thank you email from me. You're going to actually receive 2. One of them will include a certificate of attendance, if any of you can use that for professional development credit, continuing education units. That will come to you in email, and then you will get another email that includes all the links to the webinars, to lesson link, and it also includes, for those of you who do not have Sketchpad 5 and are interested in possibly upgrading or just purchasing it for the first time, it includes a promotion code that gives you a 20% discount on an upgrade or on any of the different types of licenses. So you will get an email with all of that information in it. It usually comes by Thursday as well. So if you don't get that, just let me know, send me an email, and I'll make sure you get all that information.
Do you have the promotion code to give me?
Off the top of my head? No.
I thought you might have it handy.
No, I don't have it handy. Sorry. It's off. So we're gonna end the webinar, but there's a couple questions for anyone who wants to stay on. I was just gonna let Scott ask the questions, but if you need to go, please feel free. We thank you so much for joining us. Scott, thank you so much. You obviously had a lot of information to share, and everyone was very interested, so thank you so much for doing that. Elizabeth, thank you as well for being online to answer questions. And Scott, just a couple questions pertaining to Sketchpad that I thought maybe we could just end with. So one of them was, oh no, they're disappearing on me. One of them was, can you do this iteration with Sketchpad 4? That did come up, so if you could just address maybe the difference between Sketchpad 5 and 4 iteration.
Yeah, many of these iterations can be done with Sketchpad 4. Sketchpad 5 adds the capability, for instance, of iterating pictures, of iterating text objects, of iterating graphs and loci. But many of the iterations that I did not involve those things, so many of the activities that I'm going to include with the zip file are actually doable in Sketchpad 4. The carousel, notably, is completely impossible in Sketchpad 4 because it uses a picture, and I think most of the others can be done within Sketchpad version 4.
Okay. And then there was something about how does the program iterate so quickly? I don't know if that's even a question you can actually
How does the program iterate so
So
quickly?
quickly.
We
So
spent a lot of time optimizing Sketchpad's ability to do these things as fast as possible. We give a lot of it. We pay a lot of attention to performance.
And
okay.
There's one question that we got really early on.
Yeah, I'm trying to find it.
It's I would like to have an image be transformed, but have the image be dynamic so that the image in the Sketchpad file is only a reference to a linked external file, kind of like Illustrator. To be honest, I'm not sure I completely understand the question.
So to the extent that I understand the question, the answer is no, you cannot link to an external picture. The picture actually has to be within Sketchpad. That said, it's very easy to put a picture in Sketchpad. You can simply, the best method to put a picture into Sketchpad is dragging and dropping. So for instance, the carousel horse, I'm on a Mac, so I just took the carousel horse file, horse.png, because it's a PNG file, that's a type of image file, and I dragged it into my Sketchpad window. And you can do the same thing on Windows. Drag the image you want right into the Sketchpad window, and then do whatever you want with it in terms of modifications, iterations, whatever you want to do.
Okay, I think that's all the questions that we had. So thank you everyone for joining us. We are going to end. If you've come up with a question that you want answered later, you can email me and I will make sure that we will get someone to answer it if it's not myself. Thank you, Scott. Thank you, Elizabeth. And thanks you everyone for joining us this evening. And again, expect a couple emails with links in the next day or two, and the recording and downloadable zip file will be available in the next day or two. Thank you. Good night.
Good night.
Thanks for coming, everyone.